The following is a conversation with Joel David Hamkins, professor of philosophy and mathematics at the University of Notre Dame. He has also been a professor at the University of Oxford, and his research areas span mathematics and the philosophy of mathematics, in particular set theory and the philosophy of set theory. He is the proponent of concepts as the set theoretic multiverse and pluralism, which are intriguing topic of discussion of our today's discussion. We are also delving into the concept of infinity, mathematically and more philosophically, and as well as many other intriguing and fundamental topics of debate related to mathematics and philosophy. I hope you will enjoy this conversation. This is Back to the Stone Age. Joel, would you consider yourself a mathematician or a philosopher?
Well, that's a very difficult and personal question. I mean, and it's actually a source of difficulty in my life a little bit because my original training is in mathematics. My PhD, my undergraduate degree is math, my PhD is math. So all my degrees are mathematics. And I undertook mathematical research. I've written dozens of math papers, and so most of my body of research work is mathematical rather than philosophical. But at some point, the work started becoming very philosophical and engaging more fully with philosophical ideas. And I really just tried to explore that further and ended up turning myself into a philosopher. And so, well, in New York, my original appointment was mathematics, but then I joined the philosophy faculty as well. I mean, also the computer science faculty. And when I went to Oxford, my main appointment was in philosophy, as it is here at Notre Dame. And so, okay, I guess I like to reject the premise of the question that you have to choose, because my work is really concentrated in the overlap between mathematics and philosophy. There are so many questions and topics in mathematics that have a philosophical aspect and vice versa. And that's where those are the questions I tend to be the most interested in: foundational questions or logic questions or questions about infinity and so on. And these are inherently philosophical, but also mathematical. And so I don't feel the need to categorize myself as one or the other. I mean, I'm working on the ideas and topics that I'm interested in, and those happen to be both mathematical and philosophical. And so I don't see the need to put a label on me, actually.
When and why did you started shifting toward being more of both and not only a mathematician?
I see. It's really, I mean, I've always been interested in both, of course. As an undergrad, I was taking philosophy classes as well as math classes, but my major was mathematics. But my work in set theory, and particularly the work in forcing and large cardinals, is engaged with the mathematical construction of alternative set theoretic universes. And so it is connected deeply with the philosophical question about whether there is indeed only one mathematical reality or many. And that, I think it's a deeply philosophical question. Does every mathematical statement have an ultimate truth value, a definitive final truth value? Or are there multiple interpretations of the underlying concepts in such a way that we would have multiple answers? For example, in geometry, of course, the study of geometry proceeded for thousands of years, right? With the idea that there was the one true geometry, and that's what all the mathematicians were trying to look at. But then with the rise of non-Euclidean geometry, the discovery that there were sort of alternative ways of understanding what the entire subject was about, in which the assertions come out to have different truth values. And so the topic sort of splintered. And my view is that this is part of what's happening in set theory now. We thought that set theory was just one integrated subject about the one true set theoretic universe. But what we're discovering is that there are many different concepts of set that give rise to different set theoretic universes, which have different set theoretic truths. And those truths sometimes have consequences in the rest of mathematics in terms of what's true and what's possible and so forth.
Start at the very beginning. What is set theory?
Well, I mean, set theory is a subject of mathematics that started with Georg Cantor and others at that time, say Dedekind. And of course, this is it's based on the idea that if you have a collection of things, you can think of that collection as a thing itself that's distinct from the things in the collection. I mean, the set of all elephants is not an elephant. It's a different kind of thing. It's an abstraction from the elephants. To think of the set of all the elephants as one thing on its own, right? This is what a set is. And but actually, so the topic arose sort of very gradually, and it turned out in the late 19th century that this idea, this simple idea, it's very simple, turned out to be the key to resolving many puzzling things in mathematics. For example, in geometry, in projective geometry, there's this concept of the point at infinity, right? So you have parallel lines, and maybe you want to say, well, they don't intersect, but if you add a point at infinity, that's the point where they intersect, you know. And so geometers had worked with this concept of the point at infinity, or maybe you have different points at infinity. If these parallel lines intersect at that point at infinity, and these ones going in a different direction intersect at that point at infinity, a different one. But maybe it's a bit confusing. What are these points, and how do you add them, and what to think about them? And there seemed to be a robust theory developing, but it was deeply confusing to figure out what it was about. And one way of resolving those questions, it emerged, and that was you can just define a kind of equivalence relation on the line, say two lines are parallel, right? And then you just take the equivalence class, the set of all lines that are parallel to each other, you know, and the equivalence class of a line under the parallelism relation is a set, and it can fill the role of the abstract object to which those lines are converging in the limit. And so you can, in effect, build a model of the geometry using these sets that stand in for the ideal object that you had wanted to care about. So Frege also was interested in this idea of, it's called Fregean abstraction. When you have a notion of equivalence, like two polygons have the same shape, maybe, if they're similar, yeah. But what is the shape? What is the shape itself? As an abstract object, you want to talk about the shape of a polygon. Well, this is the kind of abstraction from the equivalence relation. And nowadays, mathematics is just permeated with this quotient construction that's taking the equivalence class of all equivalent things. And that's one way to get at a representative of the abstract. It's not the only way. I mean, sometimes people confuse the quotient construction with Fregean abstraction itself, but it's not. It's just one way of making concrete, with set theory, making concrete what the abstraction is. You want an object, an abstract object that represents this abstract idea. For example, Frege also wanted to look at it with the concept of number. When do two different concepts have the same number of elements? You know, so this is connected with set theory. In other words, when are two sets the same size? And the Cantor-Hume principle is the principle that says, well, two sets have the same number of elements exactly when you can put them into one-to-one correspondence with each other. If there's a one-to-one correspondence with them, then we say they have the same number. And so the number of a set is the Fregean abstraction of the equinumerosity relation on the set. But what is the number? Well, you can take the number to be the equivalence class. You know, so the number 2 is the set of all two-element sets, or the collection, the class of all two-element sets. And this is a way of thinking about what numbers are if you implement that quotient construction, but it doesn't have to be that quotient, actually. All you want is that the number is an object such that two sets have the same number if and only if they're equinumerous, if and only if there's a one-to-one correspondence between them. I'm not sure if that answers your question or not.
Yeah, it does. I want to ask you, I've just talked about this mathematical abstractions of these mathematical objects. But now I want to ask you, do these mathematical entities that you just talked about and we are going to talk about, do they exist independent of human beings, or are they sort of dependent on the functioning of our brain? Which sort of this question is equivalent to saying, is mathematics invented or discovered?
Right. It's a famous question, and my view of that question is that people often ask the question in the way that you just did, as though all mathematics is going to get the same answer, that it's all of the same sort with respect to that question. But I don't think that's true. At least, certainly, I don't think that's true in regard to my personal experience of mathematics. I mean, the fact of the matter is that sometimes when you're doing mathematics, what you're doing feels like invention, and sometimes it feels like discovery. And it has to do, I suppose, with whether or not those particular ideas that you're working with and analyzing have already, been placed on the table. But sometimes you're inventing new concepts, new mathematical ideas, and that's the case. That's the times when it feels like invention. Or oftentimes it happens that you have a mathematical concept already that you learned from others, and you make a change to it. And that often has the character of invention. For example, I had a hand in the development of the theory of infinite time Turing machines, which is a concept of computability, using the Turing machine concept, the classic Turing machine concept, except that we allowed the computations to proceed for infinite time through the ordinals, not just infinitely many finite steps, but beyond that, they continued computing after that. And this leads to a certain mathematical theory, the theory of infinite time Turing machines, and it's quite well developed now. And there's many papers on the topic now. But I would say that in that case, my colleagues and I, Jeff Kidder and Andy Lewis and I, invented a lot of the concepts that underlie that notion of computability, that notion of infinitary computability. So it feels like invention to me rather than discovery. But if I'm working on a question, say, about infinity, about certain kind of large cardinals, and there's a question that's already been asked and it's 100 years old or something, then it feels like discovery if you figure out the answer and prove what it is, right? So maybe this view, though, could be criticized, I think, because someone could say, hey, Joel, you're just saying, if someone else already invented it, then it feels like discovery if you prove something new about that old thing, right? So it doesn't really answer. I'm just pushing it back into history, but realizing that mathematical ideas are developed in by human mathematicians in a process that's social. We tell them to each other and explain them and so on. And so in that sense, it's invented. But on the other hand, of course, the assertions themselves have a kind of sweeping universal character, which makes it seem like it would make sense that the concept of infinite time Turing machines or any other mathematical concept is existing out there totally independently of human existence and would have existed anyways, even if no one had ever thought about it. It's the same in literature, for example. Suppose, or music, say, I can imagine, the subsequent play of Shakespeare. We could talk about what the plot might be and so on. It was never written by him historically, but we could imagine that he might have written another play, and maybe it would have had, characters of a certain sort, and they would be deceiving each other in a certain way, and maybe there would be a murder and so forth. And we could tell the whole story about what he might have written, not that he did. And so does that play exist? Well, I mean, yeah, it exists. It's kind of in a way that's independent of human experience. Even if no one had ever written it, then it is a play we can imagine. And so the status of the existence of that play as an abstract object seems to be roughly similar to the status of the existence of Hamlet. The fact that Hamlet was actually written down, has been performed thousands of times, and so on, that doesn't really seem to have much to do with its existence as an abstract thing, right? And even if Hamlet hadn't ever been written down and hadn't ever been performed, then the play of Hamlet, exactly like we know it, would still exist as an abstract object in exactly the same way, because the play itself isn't, the thing written on paper or the performance. It has another kind of existence, an abstract existence. And maybe the existence of numbers and mathematical objects is something like that. And if that's right, then it seems like the existence of these things is independent of human existence.
Something that I will probably ask you about later, after we will be talking about Godel and the incompleteness theorem, is indeed
Sure.
whether, let's say, math is math all there is. Meaning, sometimes what I ponder over the consequences of Gödel incompleteness theorem makes me wonder, does this theorem imply a fundamental limit to the finiteness understanding, the finite understanding of our human brain? So does this imply that there is something else that through mathematics we cannot explain, or what?
I see. Well, that's quite interesting. So I guess my view on the matter is, well, maybe we should say a little about what Gödel's theorem says, right? So Gödel incompleteness theorem is the theorem proved by Kurt Gödel that you cannot have a computable list of axioms of mathematics that prove all and only the true statements. So for any theory that you can write down, if it's consistent, then there will be true statements that it doesn't prove. And furthermore, no such computably axiomatizable theory can prove its own consistency. So that the consistency of the theory would be one of the true statements that wasn't provable. I guess when you try to sort of connect this with the human brain and so on, there's a fundamental mismatch, because the human brain is inherently finite, but the theorem is really about infinite theories. Even it applies to infinitary theories, computably axiomatizable theories with infinitely many axioms. We could never hold all those axioms in our heads in the first place. So that the human mind is limited in its capability even of expressing certain sentences. There's only finitely many, maybe formal sentences that we could hold as objects of thought in our mind, because the Gödel incompleteness theorem is about, sort of arbitrarily long finite sentences, to all the sentences that you could express in the formal language, which include sentences that couldn't even be written down, even if you used every atom in the universe. And the proofs of those sentences maybe a sentence is provable, but the proof is so long that you couldn't possibly write it down, even if you wrote 1,000,000 steps every second since the beginning of time. And so, okay, so the theory is about these sort of potentially infinite concepts, which obviously transcend the human brain and human experience in physical reality, which is limited by space and time and so forth. So there's a kind of obvious resolution of it that way, okay? But sometimes people try to argue a little differently. So it's not just about the limitations of the human mind, but for example, Roger Penrose has argued that because in the proof of the incompleteness theorem, we can tell by looking at the theory that it is consistent, that we're doing something that the theory itself can't do, and therefore the operation of the human brain is not conforming with the theory in question, or with say, if you think about it in terms of Turing machines or computability, then you might say we can't be just running a kind of computation in our minds, because such a thing would have a sort of axiomatization that we could write down. And yet, because we can see, that the Gödel sentence is true but not provable, that's something that our minds couldn't do. So it's a fundamental. I mean, we can see that it's true, but that's something that the theory can't prove. So therefore, we're transcending what the theory is capable of. This is an argument that's sometimes given. But I question whether that line of reasoning is correct or fruitful, because I don't agree that we can just that our human minds are so capable of just observing whether a theory is consistent or not. And I just don't think that it's true. In fact, furthermore, I think that almost certainly the theory that we're actually thinking of in our minds is almost certainly inconsistent. I mean, we're not sort of perfectly logical beings and always only holding theories that are perfectly consistent. I think almost any given person has contradictory beliefs, I would think, if you drill down deep enough and uncover the principles that they think are true. People make mistakes and so forth. And furthermore, even if one takes, say, maybe we agree that the piano axioms of arithmetic are true for the intended interpretation of that formal language, in the natural numbers. Then if we do the Gödel operation of transcending the theory by adding the consistency statement and then adding the consistency statement of that and adding the consistency statement of that theory and so on. And in this way, we're building this sort of tower of stronger and stronger theories each time the theory that we have is not proving its own consistency. So we could add that statement as a new axiom and get a strictly stronger theory by doing so. So we could iterate that process. And even if we iterate it, forever, omega many times, then that theory is just another theory which also has a computable axiomatization, which we can add the consistency statement of on top and go transfinite in the iteration. And so we're going to be starting to iterate this consistency tower into the ordinals. But, as the ordinals get bigger, you will get to omega squared and omega cubed and omega to the omega and so on, eventually up to epsilon naught and then epsilon 1 and so on. And these bigger and bigger ordinals that are mind-bogglingly huge. And we can't just look at a presentation of an ordinal like that and know that it's actually well ordered and know that the theory that's arising that way is consistent. This is just not something that we're capable of doing. And there's we might have genuine doubt. And to my way of thinking, we should have doubts about consistency of these theories. It's perfectly reasonable. The only logical attitude, to my way of thinking, that we should have when we strengthen a theory, then we should become less certain about its consistency. And so as the theory is getting stronger and stronger and stronger, we should be logically getting less and less certain about its consistency. So I don't agree with the sort of mechanics of the argument to use Gödel's incompleteness theorem to talk about sort of human limitations and so on. I mean, it's a theorem about whether or not there are certain kinds of computable procedures that have certain features. And the theorem says that if you have a computably axiomatizable true theory, then it won't prove all and only the true statements. There will be true statements that it doesn't prove. And that's not about human limitations or reasoning at all. It's a mathematical statement about what in principle is possible with these kinds of formal systems.
Okay. Why I said, or let's say, why I make this reasoning is because maths is by definition the language with which we describe what appears to us our reality, physical and every possible reality, every possible mathematical reality. So it is sort of as our language indeed. So that is why I thought, that is why I had these, I think, hints at pointing to this facet of Gödel incompleteness theorem.
Right.
But now I would like to ask you about another concept which my finite mind struggles a lot trying to wrap my head around it. What is infinity to you and to your finite brain?
That's right. So, I mean, of course, infinity is a concept that has challenged mathematicians for millennia, right? It's this one very interesting aspect of infinity. There's been a kind of sea change in the way that mathematicians typically approach infinity over the years. I mean, since the ancient times. It used to be, I mean, from the time of Aristotle onwards, that mathematicians and philosophers understood infinity in a potentialist manner. So what it meant to say that a set was infinite, or say that a line has infinitely many points on it, because, well, if you have a line segment, say, you can always divide it further, subdivide it further, but it maybe doesn't make sense to have a completed infinite subdivision of the line. It's just, for any given finite subdivision, you can divide further, right? So this is a potential concept. If you have some numbers, finitely many numbers, you can always have one more by taking the next prime larger, or the next number larger, or something like that. But according to the potentialist conception, you can never have all the numbers as a completed totality. So this is the potentialist conception of infinity. And it was pervasive. I mean, almost unanimous, not quite unanimous. And there's, here and there, mathematicians and philosophers criticize the potentialist view. For example, Galileo is criticizing the potentialist conception of infinity. And one of the points that he makes is that if you're a potentialist, and you think you have sort of finitely many numbers, but you can always have more, that if you think about those possibilities as genuine, then you have infinitely many possibilities. So you actually have infinitely many possibilities. I mean, you have all of them. They're possible. The possibilities are possible. They exist as possibilities. And that's an infinite totality right there. I mean, also, he had other ideas about looking at a polygon, for example. You have an octagon. Well, you add, you can take each edge and make a 16-gon instead of an 8-gon, and then a 32-gon, and so on. You can add more and more sides. You're converging to the circle that way. And he argued, well, we can already conceive of the circle as a completed totality, which is a way of understanding the actual infinity of that the polygons are converging to as you add more and more sides. That it's not incoherent to think of the circle as a completed totality. This was already present, in the Greek geometers, the circle. It's a basic geometric concept, and we think of it as a completed totality. And yet it is, in a sense, the completed totality of the infinity that the polygons are converging to as you add more and more sides to them. So this is part of the criticism. But then the sea change happened, I guess, around the late 19th century, so that with Cantor especially, but other mathematicians at that time, started to think of the infinite collections as completed totalities, and then proceed to go on and do more mathematics with those completed totalities. And set theory is really based a lot on this idea. And today, almost every mathematician is an actualist, which is to say that they think that there's nothing incoherent about having an actually completed set, infinite set, and that furthermore, it's quite insightful and a robust idea to think of the sets, infinite sets, as existing and using them in further constructions. And it's become a core part of our understanding of mathematical reality, these sort of completed infinities. So it's really quite interesting to think historically about how much has changed in our attitude towards infinity, in the difference between potential and actual infinity.
And what is your stand on this? Are you an actualist or a potentialist?
Well, I mean, I guess to me, it's two ways of looking at mathematical reality. I mean, of course, ultimately, I'm an actualist, because if you say that there's two ways of looking, then you have to think that there's something coherent about the actualist point of view, and that's what the actualist view amounts to, is that view is coherent. So I guess I'm an actualist, except that I like to look at the potentialist viewpoint. And for example, a lot of the contemporary foundational work on potentialism it has introduced the idea of modality to potentialism. If you think about the possibilities that you could have as kind of like possible worlds, the world in which you only have this collection of objects, but then you could have more, but that's a possibility. And so you can introduce even a formal modal language where you say that a statement is possible at a world if there's a larger world where that statement is true. And it's necessary at a world if no matter what you do at all the other worlds, the statement is true. So, and then you can start looking at, well, what is the logic of these modalities? Is it true that, for example, every possibly necessary statement is already true? Or if something is necessarily possible, does that mean it's possibly necessary, and so on? So there's all kinds of questions you can ask about the nature of those modalities and what's true about them. And so that work is developing. And part of what's happened is that, of course, these are philosophical questions about the nature of possibility, about mathematical possibility, but they turn immediately into kind of mathematical questions, illustrating my earlier point. Namely, you could say, well, let's take a conception of possibility where what it means to say that what you have a possible world is maybe you build the set theoretic universe, the cumulative hierarchy, up to some level up to some stage. But it's never completed all the way. So you can always go to a higher stage and add more subsets of the sets that you have and so on, and keep building higher. So this is a conception of set theoretic potentialism called rank potentialism. And you can prove various modal truths in this. It has exactly the modal theory S4.3, which is, if you're interested, I can tell you exactly what the axiom is, but it has to do with the fact that the possibilities are linearly ordered. But there's some other concepts of potentialism. For example, the potentialism that arises from the forcing construction in set theory, which is the method that Paul Cohen had introduced to prove the independence of the continuum hypothesis. And that method has to do with starting with a set theoretic world and building a larger one, sort of sideways, and you add new subsets of sets that you already had. This is the forcing extension. And it turns out Benedict Loewe in Amsterdam and I proved, and this was why I had come to Amsterdam, was to work with him on this theorem. We proved that the modal logic of this conception is exactly S4.2, which is a different, slightly weaker modal theory. And it's not linear, is the point, because but it has a kind of amalgamation in the sense that if two things are possibly necessary, then their conjunction is also possibly necessary. But that's not true for other conceptions of potentialism. And so it's a quite rich mathematical theory, is the point I'm trying to make. We can have all these different concepts, different ways of talking about potentialism, mathematically different and precise ways of talking about potentialism that exhibit different modal truths. And so in this situation, I find it quite fascinating because the mathematical results and refinements make you realize, wait a minute, philosophically, we were being a little vague and sloppy about our idea if we thought that there was just one way of understanding the nature of potentialism. There's actually this diversity of different philosophical views to have on the nature of potentialism, and those different views are going to have different modal truths. So it's a situation where the philosophical question gave rise to a mathematical analysis whose results and refinements feed back into the philosophical issues. And I find that quite interesting.
What does not kind of satisfy me in the description, or something in the example you gave me about if you take the polygons and you keep sort of increasing the size until you get to the circle, we can consider the circle to be the totality. But what is the analogous of a circle, for example, with regards to numbers?
Oh, I see. I'm not sure I understand the question. Well, of course, if you're asking what is infinity, then, well, we have all different kinds of theories that explicate what it means to be infinite. So there's the Peano axioms of arithmetic, right? So, or the Dedekind axioms of arithmetic. Maybe it's a little simpler. Talk about the Dedekind axioms, right? And Dedekind wrote down the principles that seem to be holding of the natural numbers with the successor operation. So we have the numbers 0, 1, 2, 3, and so forth. And from any number, you have the successor, the plus 1 applied to the previous number. You can get to the next one, right? And what are the principles? Well, Dedekind told us what they are. Namely, 0 is not the successor of anything. That's one of his axioms. And another axiom is that the successor operation is 1-to-1, which means that if you have numbers x and y and they have the same successor, then they were the same number to begin with. Okay, that's what it means for the successor operation to be 1-to-1. That's certainly what we expect to be true about successor. And then the third principle is the induction axiom, or another way to say it is that it's the principle that says every number is generated from 0 by the successor operation. And how would you express that axiom? Well, you could say, if you have a set of numbers and it contains 0, and whenever it contains a number, it contains the successor of the number, then you have all the numbers in your set. This is just the induction principle. If 0 is in the set, and whenever a number's in the set, the next one's also in the set, then all the numbers are in the set. That's what it means to have induction. But I take this theory to explicate infinity, right? It's telling us the nature of the countable infinity. And what Dedekind proved quite remarkably is that this theory is categorical, which means that it has only one interpretation up to isomorphism. Any two models of this theory, if I have my numbers and my successor, I have my 0 and successor operation, and it satisfies Dedekind's theory, and you have your numbers with your 0 and your successor operation, and it satisfies Dedekind's theory, then we can match them up. There's an isomorphism translating from my numbers to your numbers, 1-to-1 and on-to way, which respects the successor operation. That's what Dedekind proved, and that's what it means for the theory to be categorical. So the axioms that Dedekind provided completely characterize what it means to have the natural numbers with successor. Okay, if you accept the axioms. And so this is an account of infinity. This is a detailed account of what does it mean to have the countable infinity. Well, what it means is to have a model of Dedekind's axioms. Okay, but there's other accounts of infinity also. For example, in the Zermelo axioms of set theory, we have not just that infinity, but the ordinals continue much taller, right? Because we have the number omega, by definition, is the smallest infinite ordinal. That's going to be a model of Dedekind's theory for the successor. But then the ordinals, according to ZFC, the ordinals keep getting taller, omega plus 1, omega plus 2, and so on. We get uncountable ordinals. And every ordinal has another ordinal which is strictly larger, and so on. And so one can view the ZFC axioms as aimed at providing a more robust concept of infinity, because it includes these taller, uncountable infinities. So if someone says, what is infinity? I would just point them to these various mathematical theories that explicate a meaning of infinity. That's what infinity is.
Okay. With regards to the model, not to the model, sorry, to the example indeed that you gave about the circle and the polygons, my puzzlement is that when you point to the circle, sort of this big regression of keep on increasing sides and getting to the circle, the circle has its ultimate stage. You cannot increase the side of a circle because it has no side, or infinitesimal,
Right. Yes.
as you would say. So sort of you have a final stage to this regression. But when I think about the numbers as you just described them in Dedekind's model or in Peano's, in another Peano's model, I think, do we ever have an sort of a totality after which we say we cannot add anymore in the case of numbers, as we cannot shorten the sides anymore in the case of circle? And the case is that um, that's not the case, because we can always increase. Indeed, a natural number, we can always add +1 squaring. So when does this process end?
I'm not quite sure I understand, because the situation seemed quite analogous to me. If you have only finite many numbers, you can always add more numbers. But if you have a polygon, you can always, bisect all the sides and double the number of sides. So isn't it basically exactly the same situation? I mean, we would want to say that the circle is the limit of the polygons as the number becomes larger and larger. I mean, part of Galileo's point was to criticize the view that it's incoherent to think of the infinite thing as a completed totality, because he was saying it isn't incoherent because we have this circle, which we think of as a completed totality. So and one can criticize the corresponding view in arithmetic just as well. It's not incoherent to think of the natural numbers as a completed totality. It's similar to thinking of the circle as the limit of these polygons. So we can think of the set 0, 1, 2, 3, and so on, all the numbers, as a completed totality. And what is the nature of it? Well, part of the nature of it is that it would satisfy Dedekind's axioms. And from those axioms, we can prove all kinds of things. Peano had famously taken Dedekind's theory and showed how to prove all of the basic number theoretic principles on the basis of it. So you can develop the theory of prime numbers and the fundamental theorem of arithmetic, and sort of the entirety of the elementary number theory can be developed on the basis of Dedekind's axioms. And so it's quite a robust account. And so this is a way is that I suppose one could say maybe that's even evidence in favor of the actualist point of view with regard to numbers. So if we imagine the numbers as a completed totality, then we get this situation where the Dedekind theory is true, and on the basis of that theory, we can prove all of these facts about numbers, and those are the expected facts, the ones that we want, and the ones that we have plenty of evidence are right. And so this can be taken as evidence in favor of the actualist view, I suppose. There's another really interesting thing. If you take the sort of finite Peano theory, finite Peano axioms, so this is the theory, it's just like Peano's axioms, except that there's a largest number. Okay, so we imagine, suppose you have the numbers, they start with 0 and they go up to some number, but we can only add and multiply them as long as the answer wouldn't be too big. So the addition and multiplication in this theory are partial functions. They're not totally defined, because, for example, if you get too near the top, then you can't add the number with itself anymore. It would be too big. So if we have this conception of arithmetic, which is a kind of potentialist conception, then suppose we have all the numbers from 0 up to some number n. Then it turns out that in this theory, you can interpret another model where the numbers go much taller. Because if you have the numbers from 0 up to some n, well, there's going to be some largest number whose square still exists. It's basically the square root of n. Let's call that number m. So m squared exists. So if I add or multiply any numbers less than m, then it's going to be defined. Okay, because of that. And so I can use m as a kind of base and consider, say, the 5-digit numbers in that base. Okay, and the point is that if I have 5-digit numbers in a base, I can add and multiply them using the usual algorithms, and I never need in that whole process to be adding and multiplying numbers bigger than m. I mean, when you carry out sort of ordinary long-handed addition of numbers, you're just adding the digits all the arithmetic is just for the, in ordinary base 10, you're always only adding one-digit numbers together and carrying and so on, but the whole process is just a process of adding with numbers less than 10 always. But the result is, many digits. And so the point is that if I know how to do arithmetic up to some bound, then by considering 5-digit numbers in the square root of that bound, I have an interpretation of numbers, and you can prove that those 5-digit numbers are going to be much bigger than the original bound. So it gives you a way, using the limited resources that you have, of interpreting a taller arithmetic. Okay. And so the point is that you should never think that the numbers are somehow absolutely limited by a bound, because if they were, then you can just use this trick to make it bigger, to make a number system that's bigger. And that number system will also, you can prove, satisfy the finite PA axioms. And then the point is that you can do it again, and again, and you can keep making it bigger as many times as you want. And in that way, you can make bigger and bigger number systems. And so there can't be a coherent way of saying there's an absolute bound on the number of numbers because of this way of thinking. And furthermore, you can prove that actually in the limit of these models, they're all cohering with one another as they get taller. It's an inherently potentialist picture. But if you take the union of everything that arises in this process, then what you get is a model of what's called I delta 0. It's a model of arithmetic in which you have induction for certain kinds of assertions, limited kinds of assertions that involve only bounded quantifiers. And so it's quite remarkable that the ultra-finitist perspective on numbers, when combined with potentialism, gives you basically an infinitary actualist model of a good theory.
Infinity is indeed a concept that defies our understanding and common sense, and there are many paradoxes about infinity, which I myself, for example, kind of struggle in trying to resolve or find an interpretation to. Can you give some of these paradoxes? For example, Achille and the tortoise. How do we resolve this weirdness in mathematics?
Right. Well, let me tell you about the Achilles and the tortoise paradox is really quite nice. So let's talk about that first. But then there's another one I want to tell you. Okay, so there's a race, Achilles and the tortoise, and the tortoise, of course, moves much slower than Achilles, but he had a head start, right, in the race. So he's and then the argument is that Achilles cannot possibly ever catch the tortoise, because if he starts running now, the tortoise is ahead of him. Then there's going to come a point where Achilles gets to the point where the tortoise had been. But by that time, the tortoise will have moved on, because the tortoise is also going. But then after that, there's going to be another. So when Achilles first gets to that first point where the tortoise was, the tortoise is farther ahead now. And so Achilles will keep running, and there will come a second point when Achilles gets to the place that the tortoise was at that earlier moment. But by then the tortoise will have also moved on again, and so on. And so the point is that the argument is that Achilles can never catch the tortoise, because before doing so, he will have to get to where the tortoise was. But by that point, the tortoise will have moved on. And so he'll have to get to that point. But by that time, the tortoise will have moved on again, and so on. And so Achilles will always be behind the tortoise. Okay. But the argument, okay, it's not very confusing from a contemporary perspective. It's obviously, the argument is wrong in its conclusion, because runners overtake each other all the time, and Achilles is definitely going to catch up with the tortoise. And the flaw in the argument maybe is that it's based on the idea that you can't take this, the moment when Achilles catches with the tortoise has these infinitely many earlier moments where Achilles was always sort of one behind. But the point is that Achilles can actually pass through all of those points in a finite amount of time. And if you pay attention to the rates at which they're running and so on, then there's no paradox at all. It's of course related to Zeno's paradox, right? Zeno's paradox is that all motion is impossible because before you move from here to there, you would have to get halfway. But before you get halfway, you would have to get halfway to the halfway point. But before you do that, you'd have to get halfway to that point and so on. And so you can't even ever get started because in order to start moving, you have to do these infinitely many things. Okay, so this paradox is similarly based in the idea that it's impossible to do infinitely many things, under that description. Whenever you go from here to there, you've done infinitely many things because you got halfway and you got halfway to the halfway point and halfway to that and so on. And so I saw a comic a little while ago. It was Zeno and his wife, is walking out the door saying, "I'm leaving you." And Zeno says, "Oh, but you can't, because before before you do that, you have to," right? So there's another paradox that I'm just writing an essay on at the moment, which I'd like to tell you about. And it's based on the axiom of choice, which maybe is a topic that might come up. And it concerns a remarkable theorem that's due to Chris Harden and Alan Taylor, which I call the nearly perfect predictor theorem, nearly perfect prediction theorem. And the theorem says the following. So you should imagine, for example, maybe we're stock traders trying to guess the opening price. Yeah. So there's some function, the previous stock price. It's only gradually revealed to us. And we want to predict the current value on the basis of the previous values. And also predict maybe how it will proceed into the future. Right. And so the problem is there a prediction process? So what is a prediction process? It takes a history of a function up to some point, and it predicts the value at that point and predicts how the function will continue. Now, if the functions are continuous, of course, then we can predict the current value because it would just be the limit of the previous one. But I'm not talking about only continuous functions because, maybe it jumps around a lot. So you might say, well, there couldn't possibly be a reliable prediction process because the previous history of the function simply has no bearing on the current value of the function, let alone how it's going to continue. But the theorem says the following. There's a prediction process which, given any history up to some point, it predicts a value at a point and how it's going to continue. There's a prediction process which is almost always right for any function. So for any function from the reals to the reals, then for almost every moment in time, t, the function is correctly predicting the value of f of t, and furthermore, it's correctly predicting how the function will continue in a small neighborhood beyond t. This is a mathematical fact. And it seems incredible. But it also gets at maybe the earlier idea that we were discussing, because the theorem uses the axiom of choice. Okay. It's not constructive. The proof is not constructive. So basically, you well order all the functions, and you look at the previous time history, and you look at the least function in the well order that agrees with the data so far, and that's your prediction. And then it turns out that you can prove on the basis of that, because it's a well order, that the places where you're wrong are themselves well ordered, because if if you look at sort of two places where you were wrong, and the earlier one was using some least function that agreed with that data, and the later one was using its least function. But the point is that the later one agrees with the earlier one, and so the prediction of the later wrong point must be higher in the well order. And what that implies is that the places where you're wrong must be well ordered. But that means that there's huge intervals and gaps between them in the real numbers. Those are the places where the prediction was totally right. So there's a prediction process which is completely correct about its guess almost all the time. Except, okay, the problem is, I say don't quit your day job because the prediction process is non-constructive. We have no idea what the predictions are. The proof is a pure existence proof. It's saying there is, in the platonic realm, there is this nearly perfect prediction process. But we have no idea what it is. And we can't prove anything about it except that it has that property. And so what I imagine is the stock traders in the platonic realm, are making bank. But unfortunately, we can't use the strategies.
They unfortunately live in the physical world, not in the platonic one. So, and what do you think? You just mentioned the platonic world, and this reminds me of the description that Roger Penrose gave of sort of the impossible triangle, where you have the mathematical world, which is sort of a superset which contains the physical world. So you have a sort of a subset of the mathematical world which points onto the physical world. In the physical world, you have a subset which is the consciousness of the working of the human mind, and it is clearly not the entirety of the physical world. And in turn, in consciousness, in the mental world, you have a subset which is again the mathematical world, and this sort of a cycle sort of loops back on itself. What do you think about this view, which is quite, I would say, popular, at least in his books that he has written?
Right. I guess I don't know anything about the physical world, actually. I mean, I live in it and I experience it and I have familiarity with what it's like day to day. But actually, I find it completely mysterious what it means, even to be physical. And I think it's wrong to make claims that we understand what it means to exist physically. I think this is a profound mystery. And the idea that somehow the mathematical world is supervening on the physical world, I think is backwards, because we can identify exactly the principles that govern the abstract existence of mathematical objects. Things seem totally clear there in a way that in the physical world, the more we learn about physical reality, the more and more mysterious it becomes. And I don't think we have any reason to think that it won't just continue to become even more mysterious in the future. I mean, the history of physics is the history of things becoming more and more weird and complicated, right? And even so, I mean, for example, maybe you have an idea of the physical reality, but actually the best physical accounts are that physical objects are actually represented by mathematical abstractions, wave functions or elements in a Hilbert space or something like that. But how can that possibly be that something physical, like an apple on my desk, is actually a mathematical abstraction, a wave function of some kind, or an assemblage of them, or something like that? I mean, I think the fact that the physical theories are expressed in those mathematical terms just reinforces my point that the reduction is going from the physical world to the mathematical one and not the other way. and it's because the physical world is completely mysterious, the nature of it. What does it mean, to knock on the desk and for this thing to exist physically? It seems completely hopeless to say exactly what that means. Or why shouldn't there be other physical realities that are just like ours but independent of it? Some uncountable infinity of them, even, or totally unconnected. And how would we know? And I think these kinds of questions really aren't going to have a good answer coming from an account of physical reality. It's a fundamental mystery. Whereas mathematical existence, I think we can give often, a more thorough account, and one which isn't getting more and more mysterious the more we know. If anything, it's the other way around.
Okay, so what is to you the mathematical truth, the mathematical reality?
I see. So, right. So there's a debate happening currently in the philosophy of mathematics, and especially in the philosophy of set theory, on pluralism and the question of whether is there only one mathematical reality, or are there many? So the pluralist view is that there's many. And I already mentioned in geometry, we seem to be pushed towards this monist view, the singularist view, for thousands of years in geometry. Then with the rise of non-Euclidean geometry of hyperbolic space and spherical geometry and elliptical geometry and so forth, and Euclidean geometry. So we have these multiple conceptions of geometry. This is a kind of pluralism for geometric truth. And maybe it had seemed that set theoretic truths were of this universe view type, for a while. But the evidence seems to be building in favor of the pluralist view. The independence phenomenon in set theory is telling us that almost every non-trivial statement in set theory is independent of the fundamental ZFC axioms of set theory. And we have these methods of constructing alternative set theoretic universes with forcing or inner models and so on. It's a quite well-developed theory. And I take it as a kind of, it's a kind of direct evidence that there are different conceivable set theoretic realities with different truths. They have different truths. We can make the continuum hypothesis true or false by forcing and so forth. And so it seems perfectly coherent that there could be different concepts of set that give rise to different set theoretic truths. And of course, once you have a model of set theory, then this is providing an interpretation for essentially all of mathematics. If one cares to interpret other mathematical concepts in set theory, we can do analysis in geometry and topology and algebra, and all of it, category theory, everything can be interpreted inside set theory. I'm not saying set theory is the only interpretation, just that it's capable of playing that foundational role. And if you have that kind of pluralist conception, then you're going to deny that every mathematical question has a definite answer, a unique definite answer. Different foundational frameworks can give different answers, even for arithmetic questions. And this is what makes it so surprising. A lot of people have the idea that, well, maybe these higher levels of the set theoretic universe have some kind of indefiniteness to them, but these people would say that at least the natural numbers are definite, 0, 1, 2, 3, and so forth. That's a meaningful, unique totality. But when you think about it a little more fully, you realize that we don't actually have very good reasons for thinking that our concept of finiteness is definite in that way. I mentioned the Dedekind axioms and his categoricity result, right? That the Dedekind theory is uniquely determining a unique arithmetic structure. But if you think about it, that his axiomatization, the induction axiom, referred to the concept of arbitrary set of numbers. Yeah, we said any set of numbers that contains 0 and is close to the successor has all the numbers. But that would be reducing the notion of finiteness to grounding it in the concept of infinite sets. And so if you thought that the concept of arbitrary set was indefinite, then you wouldn't have a very good reason for thinking that the concept of a finite number is definite. And basically the Dedekind categoricity argument is the best argument on the table, as far as I can tell. And so if that one is not providing adequate reason to think that our concept of finite number is definite, then I don't think we do have any reason to think that the concept of finiteness is definite. The point is that there are different set theoretic realities that have different incompatible concepts of the finite. And there's no way around it. I mean, maybe there isn't a single best notion of what it means to be finite. And so this is a kind of pluralist view even about arithmetic, which is really quite fascinating. There's the Skolem paradox is a famous paradox that in set theory, we can prove that there are uncountable sets, like the reals are uncountable and so on, and the power set of the reals is an even bigger infinity. And yet, if there's any model of set theory at all, then we can prove by the Levenheim-Skolem theorem that there's a countable model. So this is a countable model, and that model thinks that there are uncountable sets, but it's wrong, because that model has only countably many sets altogether, even though one of those sets it thinks is the set of all the real numbers. It just doesn't have all the real numbers in it. And so the tension between these views is called the Skolem paradox, the idea that we could be fundamentally mistaken in what we think of as uncountable or countable. And in fact, I wrote an essay a little while back explaining how it can get much worse than that. So we can have a model of set theory that has what it thinks as a finite set, but there's a larger model that thinks that set is infinite, and a larger model than that thinks the set is uncountable, and then it can become countable again in a bigger model, and then uncountable and countable and so on. We can make any pattern that we want. So by enlarging the set theoretic universe in which the set is considered, it could be finite or uncountable or countable, depending on which set theoretic background we're asking that question. And so it's really quite remarkable how malleable the concept of finite and infinite and countable and uncountable are and how highly dependent these notions are on the set theoretic background context in which they are considered. So because we have such a felicity with constructing these different set theoretic models now, we have a very advanced technology for building them. We can make these kind of crazy things happen. And the most straightforward way of understanding what's going on is that these models that we're building are sort of proxies for the mathematical reality that we might be living in ourselves, and that maybe there's a larger mathematical reality beyond the one that we take ourselves to be living in which the answers to these questions are different, and sets that we think of as finite are actually uncountable or countable and so forth, depending on which world in which they're looked at.
Could you now make a little excursion in the infinitely large numbers known as transfinite numbers? Because indeed, as we said, you can always regress to a larger number. So what are these infinitely large numbers? How can we deal with them? How do we do arithmetics with them? And also, what meaning do we give to these numbers?
I see. So, yeah, good question. So, right, it was really Cantor who discovered that there's more than one size of infinity, right? And maybe the famous result is when he proved that the real numbers is an uncountable infinity. We have the infinity of the natural numbers. The natural numbers are 0, 1, 2, 3, and so forth. And the real numbers are maybe the points on the number line, including the integers and the rationals, but also the irrational numbers and the transcendental numbers like e and pi and so forth. So the set of all the real numbers is a bigger infinity in the sense that you cannot make a one-to-one correspondence of the natural numbers with the real numbers. And the proof, well, one of the standard proofs goes like this. So suppose that the real numbers were countable, that they could be put into one-to-one correspondence with the natural numbers. Well, since the natural numbers can be put on a list, 0, 1, 2, 3, and so on, then we could write the corresponding real numbers next to those numbers. We would have a list of all of the real numbers. And then Cantor's idea was, let's write down another number, and we write down a number in such a way that the first digit after the decimal point is different from the corresponding digit of the first number. And the second digit should be different from the second digit of the second number. And the third digit should be different from the third digit of the third number. Okay. So in this way, we write down this number. Okay. There's certain issues. We have to worry about non-unique representation of the numbers. So, because some numbers have more than one representation. For example, 1.000 and so on forever is the same as 0.99999 and so on. So this repeating nines or repeating zeros phenomenon means that certain numbers, they're all rational, will have two representations sometimes. So let's just assume that when we made the list of numbers, we put both representations on the list. Okay. So now we're writing down a number so that the nth digit is different from the nth digit of the nth number. So we're going to get a real number this way, but it can't be on the list because it's different from every single number. It's different from the first number in the first digit. It's different from the second number in the second digit and so forth. Different from the nth number in the nth digit. So it's not on the list. But that's a contradiction because we assumed that all the numbers were on the list. Okay, so this is one way of proving Cantor's theorem. And so what it means is that the real numbers are a strictly larger infinity. There's a different way of understanding, a different way of undertaking a version of the theorem. If you have a set, any set, then the number of subsets of it is strictly larger than the number of elements of it. Okay. If you think of the set as a set of people, say, and the subsets are the sort of possible committees that you could make, then the claim is that there's more committees than there are people. And it's not just by saying, well, look, I mean, for every person, we could make the one-person committee consisting of only that person, but we have other committees than that. That doesn't quite prove it in the infinite case, because maybe, sure, that's a way of seeing that not every committee is a singleton, but I'm claiming that they can't even be matched up in a one-to-one correspondence. So suppose that the number of people was the same as the number of committees, that in the sense that there was an equinumerosity relation between them. There was a one-to-one correspondence associating every committee with a person in a one-to-one onto way. So let's think of that association would give us a way of naming the committees after people. Okay. So every committee is named after a person. But then let's form the committee consisting of everybody who isn't on the committee that's named after them. Okay, I mean, that's a perfect, maybe nobody's on that committee, maybe everybody's on that committee, maybe some people aren't on their committee, but others are. Okay, this certain is the committee of all people who aren't on the committee that's named after them. And now this committee must be named after someone, because we said every committee is named after somebody. Okay. So suppose this committee is named after after someone, but then that person would be on the committee if and only if they weren't on that committee, because It's the committee of all people who aren't on the committee that's named after them. So if the person wasn't on the committee, then they should be. And if they were, then they shouldn't be. And that's a contradiction. So what this means, and you might recognize in this argument, it's exactly like the Russell paradox. The set of all sets that aren't elements of themselves. It's very similar. But to say it that way would have it exactly backwards, because Cantor proved his theorem before Russell. You should say instead that the Russell paradox is like this power set argument that I'm giving. Russell's argument is like Cantor's, not the other way, because Cantor had it first. And Russell acknowledged that. Russell says in his argument even, it's like Cantor. So every set has more subsets than elements. So that means that if we have an infinite set like the natural numbers, then the number of subsets of the natural numbers is a strictly bigger infinity. Okay, but that's a perfectly good set too. So we can take the number of subsets of that set, and that's a third infinity, bigger still. And we can always go bigger. So given any infinite set, we can always make it a bigger one. And so this raises the question, well, how many different sizes of infinity are there? And I just described maybe countably many infinities, because once you have the infinity of the natural numbers, then the power set is a bigger one, and the power set of that, power set of that, power set of that, and so on. We can keep going forever, right? So that would be countably many different infinities. But if I take all of those infinities together as a set, I union up sets with those numbers of elements, that would be an infinity sort of at the top, bigger than all the ones I mentioned so far. And therefore that infinity would be bigger than all of these ones. And then its power set is bigger and so on. I can keep climbing higher on top, And it turns out to be a theorem of the Zermelo-Fraenkel axioms that for any given infinity, there are more than that many different infinities. Okay, so in a sense, the number of infinities is bigger than any one of them.
What are the implications of this result, or what does it mean to you?
Oh, I see. Well, it's fascinating, isn't it? I mean, to think about taking this, what might have been a completely mysterious concept of infinity, and then having an account of it, a theoretical account, because he wrote down axioms, and then proving as mathematical certainty certain features of it. I find that incredible way of, you don't have to just rest and wallow in confusion. You can figure things out and make progress. And isn't that amazing? I mean, this is maybe the difference between sort of philosophical investigations on mathematical topics and mathematical ones, is that philosophy is really good at raising questions, but in the mathematics we can give the answers, right? And so isn't that incredible? I think it's adding to our insight and understanding when we prove these theorems, and it's helping me to understand the nature of infinity when we prove these theorems and elucidate the different kinds of infinity that can exist in the nature and how they're connected and so forth. I just find that whole thing so fascinating, and I feel like I'm really understanding something profound about it when we prove these theorems.
Okay, so we said that let's count the cardinality of the natural numbers. Okay, that is one type of infinity. Then now we count the cardinality of the real numbers, and that's a greater infinity, as by Cantor. Is there a limit to this regression, or we are just lost to time going on and regressing to infinite time? Or is there some sort of not well-defined quantity, but some sort of conceptual bound to this regression?
So this is maybe what Cantor had called the absolute infinity. So if you think about the iterative conception of set, the sort of the cumulative hierarchy of sets, yeah. So we start with some objects, and we take sets of those objects, and then sets of objects, and so on. And in this way, we're building up the set theoretic universe. Yeah. So at any stage, the sets that come into existence at that stage are the sets whose elements already exist at an earlier stage. Yeah. And it keeps going. Yeah. And your question is related to the question of, well, how long does this process proceed for? You know, what are these stages? When does it end? Does it ever end? And it's difficult to give an answer to that question, because one of the axioms of the Zermelo-Fraenkel system, the replacement axiom, basically has the meaning of saying, well, if we can describe a sequence of stages, you know, in terms of lower things, then it's not over yet. There's going to be a stage on top of all of them. I think that statement that I just made is equivalent to the replacement axiom, saying you cannot possibly describe a collection of the stages which are cofinal in all of them. You know, the ordinals keep going beyond any kind of, and I'm not talking about finitely many. I'm talking about for any set that you have, maybe it's an uncountable set, maybe it's an enormous set. But if you have some way of associating the elements of that set with stages higher up, then there's going to be a stage on top. You know? So it's basically saying, if you can ever build a ladder of a certain height, then you can climb up that ladder and find more on top. You know? And I find this idea quite satisfying. I mean, the idea is that, look, the infinity of the ordinal numbers is so vast that at no stage can we imagine how it might be accessible to us in its totality. You know, it's quite amazing, I think. I mean, it's similar to the attitude I have about large cardinals, right? So these are these very strong axioms of infinity that are so enormous that we cannot prove that they exist. And you might say, well, that's crazy. Why would you study something that you can't prove it exists even? The point is that that's exactly part of why they're interesting. The fact that we can't prove they exist, but we think that they might exist. Because of Gödel's theorem, we know that any given theory has these theories on top that transcend it in terms of consistency strength, right? We said if you have a theory T, you know, that you think maybe is true, then the consistency assertion for that theory is something not provable in the theory. So there's a stronger theory, right? And the large cardinals are exactly exhibiting this kind of feature also, right? That they're as we go up in the large cardinal hierarchy, then the existence of the higher cardinals is implying the consistency of the existence of the lower cardinals. And so it's exhibiting the predicted phenomenon of Gödel's theorem. And yet, is that a reason to believe that they exist? No, I think, because as far as we know, it's consistent to think that there aren't any of these large cardinals at all. But yet the picture of mathematical reality that you get when you assume that there are these extremely strong axioms of infinity, these extremely large cardinals, it's amazing. If there's certain kinds of large cardinals, then you get these sort of regularity properties, even for sets of reals. If there's enough large cardinals, then it turns out that every projectively definable set of real numbers has the determinacy property, which has to do with certain infinitary games. And there's other very natural regularity properties that hold for definable sets of reals if you have these large cardinals way up there. So it's kind of remarkable, actually. that the existence of these enormous infinities causes certain highly regular and welcome, desirable consequences down low, even. So a lot of large cardinal set theorists take that as evidence that they really exist. We're getting these answers, systematic and coherent and welcome answers to these questions that people had had, for 100 years about sets of reals. So it's really quite remarkable, I think. And that, I think, should probably be taken as sort of scientific evidence in favor of the large cardinal existence.
Sometimes, sometimes when I think about the concept of infinity and these sort of beyond conceivable quantities, one thought that arises to my mind is, and again, now I have to bring into discussion the finiteness of the human brain. I don't want to talk trash about us, but what I believe is sort of as a destructive belief. Some days, other days I have other beliefs, but in some days I do believe that to us humans is fundamentally impossible to truly grasp the concept of infinity, because one of the properties of infinity is the non-ending, is the endless iteration of something, or is the endless countability of something. And since this endless implies the sort of manipulation of the time dimension in a way that you say it keeps on going forever in time, and we cannot grasp the time dimension as easy as our space dimensions, because I can say I can be in this part of space or I can be in this other part of space, but I cannot choose in which part of time to be. I can simply flow with time. I can simply go on and follow the line of time. So to me, sometimes this concept of infinity kind of tells me, as long as we do not have a grasp, or we do not have decidability over the whole of time, we will never be able to grasp, to truly grasp with our mind the entirety of infinity, because infinity is strictly related to the never-ending, to its never-ending property. What do you think about this?
Right. So sometimes when I'm teaching people how to count in the ordinals, I talk about it in this temporal way that you were just describing, because I feel that it helps them. So, for example, like if we imagine, well, let's try to count up to omega. Say, how do you count to omega? Omega is the first infinite ordinal. So how do you get there? Well, you start counting 0, 1, 2, 3, 4, 5, and so on. Yeah, everybody knows how to count in the natural numbers. And then omega is the first number that comes after all of those numbers. Now, sometimes people object, well, how could you ever get to omega? Because it takes forever to say all the earlier numbers and you would run out of time before you got there. And one way of addressing that concern is by saying, well, you should count faster and faster. So you should say, give yourself a whole day to say the number 0. Okay. And then the next day, in a half a day, you say the number 1. And then a quarter of a day, you say the number 2. Okay. And an eighth of a day, you say the number 3, and so on. So if each next number is said in half the time of the previous one, as the numbers get bigger, then, well, that's a geometric series, and it sums to 2. So by the end of the second day, you've said all the numbers, and then you can say omega after that. And you can go on omega plus 1, omega plus 2, and so on, and continue. Okay. Some people find that helpful, but I believe it's a mistake. And I don't believe that the mathematical concepts should be thought of as existing in time. I think we should understand the structure of the ordinals on its own, and it's a mistake to put it into time. And that it has its own order, which is the order of the ordinals. And for example, the numbers aren't getting closer and closer together as you go up, and yet there are numbers after them. And that is a very interesting mathematical structure, which is mind expanding to consider. It doesn't fit into the real line, precisely because of the objection that had been made that you would run out before you got to omega, right? If the distance between all the numbers was 1, which it is in ordinal arithmetic, then when you get to omega, it's infinitely far away from the starting point, and that's fine. That's the nature of that mathematical structure. And omega plus 1 is 1 further, and so on. And then you get to omega plus omega, and so on, omega squared, and eventually out to the uncountable ordinals, okay? And it's mind expanding, in my view, to abandon the connection with time, which actually is not relevant anyways for the abstract mathematical structure of the ordinals. So there's many other kind of mathematical structures which can't be mapped into the real numbers or into other more physically familiar structures. Those are just too limiting. And so I would encourage someone who feels that somehow these more abstract or larger mathematical ideas have to be related to physical reality somehow. They're making a mistake, and they're missing some of the beauty of the mathematical ideas when they insist upon that.
Okay. Well, other than the infinite concept that puzzles me a lot is also the concept of irrational number. So never-ending sequences of decimals. Now, what is the difference, let's say, conceptually? Of course, pi is different than omega. But what is the difference between an infinite sequence of decimals and the infinite omega or other cardinals? Because sometimes when I think about the real numbers, including the irrational numbers, I think, okay, but wait a second, pi is not real in the sense as we in the adjective, in the description that I would give of real things in this physical world. It's not real. I cannot point to a line and say, okay, this is pi. So how do you feel about this?
Well, it's really very interesting. I mean, I would want to talk about Alan Turing's paper in 1936, where he wrote on computable numbers and the Entscheidungsproblem. So he introduced the idea of computable real numbers, which I think is addressing some of what you said about the number pi. So for Turing, in his paper, he said a real number is computable if we have a finite computation procedure that would systematically generate the digits of that number, which we do in the case of pi. We can write down a computer program which will give you as many digits as you want. If you let it run long enough, you'll get as many digits as you want. And that's a sense in which I think addresses your concern that pi, even though the digits go forever and they don't ever repeat and so on, nevertheless, they're following a pattern in the sense that they can be generated by a finite computational procedure. Now, not all real numbers can be generated by such a procedure because there's only countably many programs. And so only countably many real numbers will have computation procedures like this to generate their digits. There must be some numbers, some real numbers that we cannot generate by any computational procedure because there's uncountably many real numbers. It's interesting to me to think about, however, the sort of contemporary view of computable analysis, which is the theory of doing calculus but with a view to computation, So we want to look at computable functions and computable real numbers. And, if it's continuous, then for every computable epsilon, we want to find computably a delta, to witness the continuity property and so on. We want to compute these things. That's what computable analysis is about. And computable analysis has abandoned Turing's definition. They've pointed out that's not actually what we want. And the reason is connected with I just recently read an essay, a blog post of Timothy Gowers, in which he's defending the decimal expansion conception of the real numbers. It's not usually how we think about what a real number is. I mean, it's the kind of elementary school definition of a real number, but usually when we prove that the real numbers exist, we do so with, say, Dedekind cuts in the rationals or equivalence classes of Cauchy sequences. And we have a variety of constructions, but sort of decimal expansion isn't usually on the list. But Gowers was defending this conception and explained how to prove the expected theorems that you got a complete ordered field when you consider decimal expansions of numbers. And in that sense, it's connected with Turing's idea, and the objection that one might make to it is the same as the objection that the computable analysis make to Turing's definition. Namely, you can't add. If you have two numbers, A and B, and you have their decimal expansions, what you want to be able to do is, so you have a computable procedure that gives you A, maybe A is the number pi, 3.1415926, and so on. And maybe B is some other number. And you want to produce from those programs a program that computes the digits of A plus B. You can't do it. There isn't one. You can prove there isn't one. You cannot add numbers computably if you think of the numbers as being constituted by their decimal digits. It's not a computable process. And the reason is, well, if you might think, well, how do you add? Isn't it easy? It's trivial, right? You just line up the decimal points. Okay, and you can add the integer parts, that's no problem. And then the rest, you just add digit by digit, right? And those are going to be the digits of A plus B. But the problem is, maybe there's a carry. So maybe you're getting a lot of 9s in a row. And you don't know if it's going to overflow or not. Maybe you had, maybe the sum was 3.21499999999, but you don't know it's going to go forever with all those 9s. Maybe it's going to become a 2 later on. Or maybe what's going to happen is the digits way out there are going to add up to more than 10. And so all the 9s are going to turn to 0, and you're going to have to add 1 to the previous one. And you don't know which. There's no computable procedure that will tell you whether or not the 9s are going to end one way or the other. And so you cannot produce computably the digits of A plus B. And you can prove, as a fact, there is no computable procedure which, given programs for A and programs for B, produces a program for A plus B. It's impossible. It's like the undecidability of the halting problem. You can code the halting problem into it. And so that's a similar reason to object to the decimal representation account of the real numbers, because if you list out all the digits of one number and then all the digits of another number, then you want to say, well, can we from that, if we have oracles for those digits, can we produce computably from it the digits of A plus B? And the answer is we can't, for the same reason, because we don't know if these carries are happening or infinitely often or not. And so we can do it on a case-by-case basis, but the point is that we can't, there's no uniform procedure that always works. And so this is connected with maybe how should we think about what real numbers are? Is a real number a decimal expansion? Well, that's one way of understanding it. But if you insist on it, then you can't computably add real numbers because of this. And the other conceptions, like the Cauchy sequence representation, is maybe a little bit better. But what a real number is it's approximated by pieces of those decimal expansions. And what we can do is, if we have A and B, then we can add and get numbers that are closer and closer, as close as we like, to A plus B. And that's basically the proof that you can computably add with Cauchy sequences, or with Dedekind cuts, you can computably add if the presentations are given to you in a certain way. And so these other conceptions of what real numbers are allow for computable, all the standard functions on the reals, not just plus, but times and exponentiation and tangent and sine and e to the x and log functions, and all of those are computable functions if you present the reals in the right way. But if you understand reals as represented by computable programs for enumerating the digits, then none of those functions will be computable. I don't know if that helps or not.
Yeah, I just find it funny when I think about it that we use the adjective real to define numbers as equivalence classes of Cauchy sequences. Okay, doesn't sound very real in the strict sense of it, but of course. I wanted to ask you, I have read recently a book by Rudy D. Dicker,
Rudy Rucker.
Rudy Rucker, yes. And basically he's reporting these words by Cantor in the description of a set, which probably are more philosophical than set theoretic. And it says that a set is a many which allows itself to be thought of as a one. What are these words? What do they mean?
Oh, this is a completely standard understanding of what it means to have a set. Yeah. So the many is referring to the elements of the set, right? And the one is referring to the set itself. So if I take the set of all elephants, I have many elephants, but I think of those many elephants as when I put them into a set, then I think of there being one set of all the elephants. Yeah. So I have many elephants, one set of elephants. So I want to think of the elephants collectively as a one, the one thing which is the set of elephants. So I think that's what that phrase means. But it's also, I think, goes back to Cantor. Cantor used phraseology almost exactly like that. I mean, in German, of course. But it's the main starting point of what set theory is about, is when you want to do that idea. You want to think of many things as a single collection of things, as a set.
Do I have to think about a set for this set to exist?
Well, if you take that line, then there would be only finitely many sets and so on, and all the ideas about countability, uncountability, and so on, all of that would be false, right? So I mean, it's related to the question of whether these mathematical objects exist independently of human understanding. Are there only finitely many numbers because eventually humans will die out and each of them is, every person has only ever thought of finitely many numbers in their life? And so is that a reason to think there's only finitely many numbers? Well, okay, that's a certain extremely limited conception of what mathematics is about. And I think it's not a very robust one because the numbers won't be close under successor that way. And maybe people have thought of numbers, but not every smaller number has been thought of. I mean, I've thought of a googolplex that's 10 to the Google. It's an enormous number. There's just far too many numbers less than it for them all to have been conceived by someone. There's not that many people who have thought of that many numbers for all of the numbers less than a googolplex to have been the object of thought. In fact, I've argued that it's impossible for most of the numbers less than that number to be the object of thought at all. But that doesn't mean that those smaller numbers don't exist and so on. I think that that's taking that line is you're gonna end up with a mathematical theory that isn't very satisfactory and has all kinds of weird unintended effects and so on. I don't think it's a good way to think about the nature of mathematical existence, to tie it to these contingent things about whether someone ever thought about that number.
Okay. You mentioned before Cantor's theorem, saying that every set has more subset than elements, which then the implication is, or what comes out is that the cardinality of the reals turns out to be greater than the cardinality of the natural numbers. And now I want to ask you, Cantor also proved that infinite sets are similar to subsets of themselves. So they are equinumerous to proper subsets of themselves. And now, if someone just followed this chain of reasoning, I would say, wait a second, isn't this sort of a contradiction, or isn't this counterintuitive to our understanding?
So this is exactly a point made by Galileo in Two New Sciences in his dialogue with Salviati and Simplicio. Simplicio makes exactly the objection that you just made. Namely, the context was they're thinking about the numbers, 1, 2, 3, 4, and so on, the positive integers, and the perfect squares. Yeah, so these would be the numbers 1, 4, 9, 16, 25, and so on. These are the perfect squares. And on the one hand, it seems like there's way more numbers than perfect squares because there's all the numbers in between. You know, between 25 and 36, there's a whole bunch of numbers, and between 36 and 49, there's a whole bunch of numbers, and so on. And the squares are getting less and less dense, even spaced further and further apart. And so it seems kind of intuitive that the number of numbers should be maybe greater than the number of squares. But on the other hand, we can make a correspondence because we can associate every number n with its square, n squared. So we can associate 1 with 1, and 2 with 4, and 3 with 9, and 4 with 16, 5 with 25, and so on. And that's a one-to-one correspondence. And so therefore, you might think, well, if you believed in the Cantor-Hume principle, then you would say that the number of numbers is the same as the number of perfect squares. And so this is this tension between the Cantor-Hume principle and what's called Euclid's principle, which is the whole is greater than the part. You know, so they seem contradictory. And Galileo's resolution of this, well, he didn't have a resolution. He threw up his hands in confusion and said, therefore, we don't understand infinity, and it's wrong to make size comparisons in the infinite case. Okay, this was Galileo's response. He was so close to Cantor's ideas hundreds of years earlier. But instead of taking Cantor's approach, he gave up, in a sense. It's really quite amazing. Whereas Cantor takes the Cantor-Hume principle as fundamental and says, therefore, the strict form of Euclid's principle is just not true for infinite sets. This is a feature of infinite sets. It doesn't obey the strict form of Euclid's principle, the strict form meaning that the whole is strictly greater than the part. If you just say the whole is at least as great as the part, then there's no contradiction at all. And this is fine for Cantor. So you don't have to, if you adopt the Cantorian framework, where you have the Cantor-Hume principle, you know, so sets are said to have the same size if they can be put in one-to-one correspondence. Then you're still going to have the reflexive form of Euclid's principle, namely, the whole is at least as great as the part. Okay, whenever you have, one way of saying it is that whenever you have an injection from A to B, you know, a one-to-one map into B, but maybe it's not onto, you know, then B is at least as great as A. Yeah, for Cantor, that's the definition of what it means to say at least as large as. But then you need to prove something further, and there's a remarkable theorem about this. Namely, suppose you have two sets, A and B, and each of them is at least as large as the other. You know, in the sense that each of them has a one-to-one correspondence with a subset of the other one. Does that mean that they have the same size? I mean, if you take the words with the sort of usual meaning, then of course you would want to say if two things are at least as large as each other, then they have the same size. But this is a mathematical question, right? If you have injections from A to B and from B to A, does that mean that there's a bijection between them? Does that mean that there's a one-to-one correspondence between A and B? And it's not obvious. It is definitely not obvious. But it's true. There's a theorem called the Cantor-Schroeder-Bernstein theorem, which exactly proves that whenever you have a one-to-one map from a set A into B, and you also have a one-to-one map from a set B into A, then you can combine the maps together in such a way to make a bijection, a one-to-one and onto correspondence between A and B. So it means that the reflexive form of Euclid's principle is very robust because of this theorem. You know, if two sets are at least as large as each other, then they have the same size. That's a theorem of mathematics, the Cantor-Schroeder-Bernstein theorem, which is not obvious. It's a non-trivial theorem, but I think it's very important for the success of the Cantorian conception that this theorem is true. If it weren't true, it would make the concept of number that the theory is providing much less satisfactory. Yeah, it's quite interesting. So one can talk about computable versions of this principle also. If you have sort of computable functions, can you find a computable bijection? And this in other mathematical contexts, for example, if you have two orders and each order has an order embedding into the other one, does that mean that they're isomorphic? And the answer is no, it's not true in general in that sense. So for any given mathematical conception of structure, you can ask, does it have the Cantor-Schroeder-Bernstein property, in the sense that if you have two structures, two instances, and each of them is isomorphic to a substructure of the other, then does that mean that the structures are isomorphic? And it's not always true. But in some cases it is true, and in the sort of pure set structure case, it is true, and that's exactly what the Cantor-Schroeder-Bernstein theorem asserts.
Said you mentioned of sum being the sum of something being greater than the sum of its part, and this is a sort of a description that in the book I read about Infinity of the Mind of Rooker. He says in a section dedicated to quote unquote God, one of the characteristics of the properties of God must be the fact that it is inconceivable. So God must be a many, which does not allow itself to be thought of as a one. And now I want to ask you, what is to you this definition of God, or if you believe in any religion of any sort, or what to you is the one whose sum is greater than the sum of its part?
Yeah, I'm not sure. I'm not religious myself. And of course, I mean, he's calling it God, but I mean, this is not a conception of God that like would be part of any of the standard religions that people customarily talk about, right? And it reminds me of Gödel's. Gödel has this famous proof for the existence of God, where he defines God in a certain way. It turns out to be an ultrafilter on the natural numbers. I mean, if you unwrap the definition, and he proves that there is one, and so it amounts to proving God. So it's turning into some kind of mathematical fact, and so right, I guess I don't want to talk too much about Rudy Rucker, because although I know of that book, I haven't looked at it in many, many years, and so I don't quite remember what it was that he was writing about it. But I'm not sure I find it so interesting to give these mathematical definitions of what it means to be God. I just don't think this is really shedding any light at all on what people would ordinarily mean by God. And maybe it's interesting mathematics and so on, but I don't really like the terminology used that way, and so I'm not sure I have much to say about it. I'm sorry.
Okay. Then, well, you also mentioned that earlier on the very debated on continuum hypothesis, which has led to a lot of controversy in the world of mathematics. Can you describe it very briefly, and is it proved or not?
Oh, I see. So the continuum hypothesis was the problem that has been in set theory from the very start, from Cantor's time. He was troubled by the question because once you prove that the real numbers are a larger infinity than the natural numbers, then it's extremely natural to wonder whether there's any infinity in between. Is it the next infinity or not? And the continuum hypothesis is the assertion that yes, it's the next one, and there's nothing in between. And what's it fascinated Cantor. I mean, he dedicated his life to trying to answer this question, but he never answered it. In part because the answer that we know now is very subtle and required quite a lot of technical developments of the subject in order to get to the state that we know now. So it's not surprising that Cantor wasn't able to answer it at the time. It's a very difficult question. Cantor made progress, though. He proved certain instances of it, namely that certain kinds of sets, for example, closed sets can never have an intermediate size. So every closed set is either countable or else it's equinumerous with the real numbers. This is not obvious, but it's true. And one can prove it using what's called the shorter, what is it? The Cantor-Bendixson process. So if you have a closed set of reals, maybe it's a convergent sequence, or maybe it's a convergent sequences where those points on the sequence also have convergent sequences converging to them, or something like that. So you can imagine some complicated closed set. But some of the points might be isolated in the sense that there's no point nearby. You can draw a little disk around them where that point is all alone. Those are called isolated points. So the Cantor-Bendixson process is, given a closed set, you throw out the isolated points. And now you have a smaller closed set. And now maybe you threw out the isolated points, but maybe some of the new points in the derived set become isolated. So you want to throw out those isolated points as well. Yeah. And you can do it again and again. Maybe every time, when you throw out the isolated points, you still have isolated points left, and so on. And what Cantor and Bendixson proved is that if you do this process, then at some countable ordinal stage, it might go transfinite, but it will be a countable ordinal stage. You'll get a set that doesn't have any isolated points left. Maybe because it's empty, or maybe because it's what's called a perfect set, which is a closed, non-empty set that has no isolated points. And now you can get the result, because Cantor proved that every perfect set is equinumerous with the whole real line. And so if you have a closed set, if you go to the perfect set, then the whole set was equinumerous with the real line. But if it stopped because it became empty, then the set must have been countable because you only threw out countably many points. So every closed set is either countable or equinumerous with the whole real line. So this is an instance of the continuum hypothesis, but CH is about all sets, not just closed sets. So Cantor made some progress. It wasn't until 1938 that Gödel had proved, so this is many decades after Cantor, Gödel proved that you cannot refute the continuum hypothesis from the Zermelo axioms because he built a model of the Zermelo-Franco axioms in which the continuum hypothesis is true. This is the constructible universe L. So Gödel's universe, Gödel built a model of set theory, a set theoretic universe in which the continuum hypothesis is true. So therefore, we can't refute it from the axioms. But that didn't settle the question. Maybe we could, it doesn't provide a proof of it. It just shows that it's consistent, that it's true. And it wasn't until 1962 or 3 that Paul Cohen proved the dual version using this forcing method that I mentioned earlier, namely, given any model of CFC set theory, we can build another model in which the continuum hypothesis is false. And therefore, we can't prove it either. So it's neither provable nor refutable. It's independent of the ZFC axioms because of these two facts. So now we know also you can force CH to be true or force it to be false. You don't have to go to L. There's lots of places, lots of other universes in which CH is true. You can make it true or false as much as you want by forcing, given any model of set theory, there's a bigger one where it's true and a bigger one where it's false and so on. You can turn it on and off like a light switch. And in my analysis with Benedict Lobe on the modal logic of forcing, we call these kind of statements switches, the ones that can be turned on and off by going to a larger universe. You can make it true and false again, as much as you want. Okay. So the question, though, is if you know that the continuum hypothesis is independent of the axioms, then if someone was a universalist, if they thought there is a single one true universe of sets, then it's meaningful on that perspective to ask, well, is it true or not? There, in the one true universe, is it true? And because the independence result is really just telling you about the weakness of your theory. It's not telling you about whether the thing is really true or not. That's the view of the monist who believes in one true universe. If you're a pluralist, though, then the forcing arguments are really, telling you quite a lot about the nature of the continuum hypothesis. Maybe that it's true in some of the set theoretic universes and false in others, and that's the answer to the CH question, is that it could be true and it could be false depending on what your set theoretic background is, and in the pluralist context, that's a perfectly good answer. But it's not only just that it's sometimes true and sometimes false, because we also know in a quite detailed way how to make it true and how close the universe is where it's true. For example, if you have a lot of large cardinals, then there's a forcing extension in which you still have all those large cardinals, and yet CH is true, and yet CH is false, however you like. Or if you want to preserve other set theoretic features, you can often do it. This is the nature of these forcing arguments, is that you're producing these set theoretic universes that exhibit certain features. CH is often one of the features, or not CH. And we can often build these models to order. If you say, well, I want not CH, but I also want this and that and the other thing, then we can often do it because we have such a developed technology for constructing these models. Okay, and this is all part of the sort of pluralist way of looking at the answers. All of that information is the answer. We don't know everything, of course, but we know quite a lot about how it can hold or fail in the multiverse, and that's what the answer to the CH question is. Okay, but the universes are saying, no, there's one true universe, and we're trying to figure out if it's really true there or not. And it points to a sort of difficulty for the universes because there's no mathematical argument that they can give us. It has to be philosophical because the thing is independent. They can't prove it one way or the other. It has to be a philosophical argument for why this universe is the one true universe or this other one. And it becomes very difficult for them to mount such an argument, in a way that's convincing. Because the pluralist could just say, well, that place sounds really great, but it doesn't mean it's the only one, right? Just because you have a shining city on the hill doesn't mean it's the only city, right? And so this is the tension between the monist and the pluralist point of view.
Do you have a favorite universe of set theory?
A favorite one? Well, I'm a strong defender of pluralism, and so I guess I should say no, I don't have a favorite one because there's many, but actually it's really hard to pin down just one anyways. You can write down a theory, but any given theory, of course, has many, many models of that theory, and it's hard to tell them apart. And if you have different set theoretic conceptions or different set theoretic. Even if you have one model, there could be another model that has exactly the same truths to it. And so it's difficult to say, what you would, it's difficult to refer in a definite way to particular models. And even when you do so in the context of a theory, then because the theory itself has different models in which it's interpreted, then the referent of that pointing at would be different. And so I would say it's impossible to have a favorite model, but rather you could have, favored axioms and so on. Maybe that's a more sensible way of talking about it.
Can I ask you why was infinity sort of a hostile concept to many mathematicians, especially in the past? For example, mentioning the words of Kronecker, he said that unless we can give a definite means of constructing the mathematical things about which we talk and think, we are reasoning, we are talking nonsense and not reasoning at all. Why has infinity found, I mean, intuitively, I can point down to a couple of reasons why has infinity found a lot of resistance, I would say. But what are these reasons?
I'm sorry, I don't quite get the question.
Why was infinity hostile to many mathematicians that was basically sort of, let's say, not regarded as a definite mathematical object with which a mathematician could elaborate and could produce consistent mathematics?
Yeah, I'm not sure that I would know the answer to that. I mean, you'd have to ask them, right?
That's true. That's true.
Uh, uh,
They are not alive anymore,
I mean,
many of
certain
them.
aspects of it were confusing before they were better understood. And for example, Galileo's case, I think, is really quite good. Because he just lays it all out there, what his confusion is, and it has to do with this tension between what we now call the Cantor-Hume principle and Euclid's principle, and he just couldn't get past that, right? And he's quite explicit about it through his character Salviati, and who's the sort of stand-in, one thinks, for Galileo himself, because he's the sort of clever one. And but so that's, I think, maybe a good place to look for why people were resistant. And he's finding it because of this tension. Yeah. But this is maybe different from the potential actualism, the potentialist and actualist dispute, which Galileo was also involved with and is also in those dialogues. But there's huge literature, I mean, going all the way back to Aristotle, right? And many extremely prominent mathematicians were on the potentialist side, quite insistently so. And whereas now, it's hard to find someone who's like that, except for, of course, there's many cranks who are potentialists and insistently so. But by and large, most mathematicians are not on that potentialist side anymore. And the fact that there have been such amazing achievements in mathematics in elucidating problems that were formerly open, but which are now completely solved, I would think is a reason to see that the hesitancy, the historical hesitancy, was unjustified, and they were just wrong about it. Because if they had adopted the actualist point of view, maybe they would have made similar progress, right? And I mean, okay, this on YouTube you can find many people, some prominent people, talking about ultrafinitism and criticizing infinity and so on in a way that I find amounts to kind of simple skepticism, they're saying, well, we don't have good reason to think in these infinite things, and is it logically coherent, and so on. But I tend not to take those criticisms very seriously because they're not offering me any additional insight. I'm not learning any mathematics from the criticism, whereas I was learning a lot of mathematics from the taking the infinity seriously side, from the actualist side. And so for me, the only way the criticism can be successful is if it's providing more mathematical insight or identifying, incorrect conclusions, like if there's some inconsistency coming. But the criticisms are never doing that. They're just like kind of moral scoldings. They're like it's a kind of moral wrong to work with the actual infinity or something. But that doesn't get me anywhere. I don't learn any mathematics from being scolded. Or it's often similar, for example, in the dispute between constructive mathematics and classical logic. When you give a mathematical argument and a proof of a theorem and someone says, but you use the law of excluded middle, then okay, that could be true. I use the law of excluded middle because I use it freely, because I view it as a law of logic and a truth, a fundamental truth. Okay. And and so to me, to say merely that the argument wasn't constructive in accordance with the laws of intuitionistic logic really tells me nothing of value, right? The valuable thing would be to say, hey, if you do the argument constructively, then you can extract more information from the proof. And that's often true. Okay, that's a legitimate criticism to make. If someone says, your proof isn't constructive, but there is a constructive version of it, which gives us more information. Okay, that's a valuable thing that would add to the conversation. Yeah. But for someone to just criticize the use of infinity without giving me more mathematical insight, then I don't have to take that criticism very seriously, I think.
You mentioned the law of excluded middle. Correct me if I am wrong, which I might be. It says that a statement can be either true or false.
That's right. Yeah.
Okay.
So it's the logical principle that says either P or not P.
Okay.
That's
Henry Lebesgue, many years ago, he stated explicitly that he was not convinced that a statement about an infinite set follows the law of the excluded middle. So he didn't think, or he was not convinced that a statement about an infinite set is necessarily true or false. He pointed somewhat vaguely to a third possibility between truth and falsity. Horry also said that there may be nothing but nonsense in any assertion about an infinite set. What do you think about this thing, which sort of under a logical point of view is outrageous to think and even say, because of course something is either true or false.
right. So, I mean, to me, I don't find the discussion about law of excluded middle particularly connected with infinity. I mean, in the way that you described Lebesgue. I mean, it seems to me the debate about non-classical logic can be undertaken even when you're not talking about infinite sets. Although it seems to be a theorem of some of the constructive mathematical systems that the law of excluded middle does hold, for instances, for certain kinds of properties made about the natural numbers and so on, you can just prove the corresponding instances without assuming law of excluded middle. You can prove the relevant instances of it in the simple finite cases anyway. And so I suppose that's a way of giving some substance to the view that you were just talking about, namely that the violations of LEM are sort of can be having to do with infinite sets more than finite ones. Okay, but it's not strictly true in the generality. So I guess, yeah, I don't. there's a very well-developed theory of constructive mathematics in which mathematicians are looking nowadays, for example, at these toposes, which are sort of mathematical structures of a certain kind connected with category theory, in which there's a way of interpreting the truth of statements in an internal way, and which obeys only the constructive logic and not classical logic. So in particular, in the internal logic of a topos, you don't necessarily get the law of excluded middle being true. And so the community of constructive mathematicians are, working in constructive mathematics are figuring out how truth works and mathematical truths work in these toposes. And it's really quite interesting for them, I think. And it's a very developed theory and a whole, hundreds of people working on these kind of things. My own thinking on the matter is that the particular mathematical questions and topics that I work in are less connected with the areas in which this constructive mathematics phenomenon is arising. And so, for example, I don't know of any instances of questions of the sort that I've spent my life working on where one gains insight into the mathematical questions by thinking constructively. It's just never happened with me that I've felt that I've learned something by insisting that the logic should be intuitionist instead of classical. And so I just, I guess I don't often find it so compelling of a perspective to abandon classical logic. It seems also that oftentimes when people want to give up classical logic and go to intuitionistic logic, it's because of concerns, say, about computability or uniformity and so on. And in those cases, it seems, to my way of thinking, that we don't have to actually change the logic at all, and we can just talk about computability and uniformity, which classical mathematicians do in classical logic, without changing the logic. And it's such an irritating radical change to give up the law of excluded middle and double negation elimination and things like this. It's just an unnecessary change in those cases when we can just talk about whether the thing is computable or uniformly computable and so on, if that's really what the issue is. Okay, it's not always the issue, and sometimes there's something deeper going on. And in those cases, the constructive logic does seem natural, as I was saying, in those toposes that I was talking about. But in these other cases, it seems a bit gratuitous and indulgent, frankly, to change the logic in that way, when one can just keep classical logic and talk about the relevant notions that are really being considered.
How do you come to terms with the fact that maybe most of the interesting questions that you are working with, that you have spent maybe a pretty big part of your life working on, might never find an answer?
Oh, I see. Now, that's quite interesting. Yeah. Well, I mean, how can one but be already to terms with it, because they don't have answers right now? Okay, so there's certain questions I might be thinking about, and maybe they're never going to get an answer. I don't know if they will. I think probably most of the questions that I'm asking will get answers eventually. I'm just happy whenever I can make progress at all. I mean, it's such a joy. You have a question, and at first it's very confusing, and you feel that you don't know anything, and you talk with someone. Maybe there's a visitor in town, and you spend a day, walking around, talking about it, or sitting in the library or at the chalkboard talking. And gradually understanding emerges. Maybe you understand an example a little more deeply, and then you see, aha, there's something deeper going on. And gradually one attains some understanding about something that was previously very confusing. And that's one of the great pleasures in life. I think I feel very fortunate to have had these kind of experiences. I feel that it's very meaningful when it does occur. Okay, the fact that some problems will never get an answer is somehow beside the point and kind of not part of it at all. I already have so many questions I'm working on. I won't have time to answer all of them, but I'm just happy in the few cases when I do come to an understanding, and that's really great. I love it a lot.
Do you believe that there is more than maths that permeates reality?
Um, well, there's all kinds of other things than math, right? I mean, there's music and literature and so on. So of course there is, and food and good friendship and so forth. Not to
In
mention
sense,
sex and other things that are really great. So,
in sense, maybe more. I don't remember who was talking about this concept. Probably Max Tegmark. He was saying it might also be the case that everything eventually is just mathematics. So um, deep down, everything is just governed by a bunch of equations and mathematical objects. Um, do you believe that's the case, or do you believe there is more than that that we just cannot grasp at the moment, or maybe never?
well, I mean, I guess it's related to these things I was talking about earlier with physical reality, where some of the physical accounts of physical reality are, everything is really just a wave function, which is a kind of mathematical object. We're all just things in some Hilbert space and other. But um, I guess I find that those ideas a little bit unfulfilling in the sense that they're not really telling me what it means to exist physically, which, as I've said, is a profound mystery. Even if one has a kind of complete mathematical account describing the nature of physical interactions, I think it still doesn't tell us what it means to exist physically, because it seems like those mathematical equations and those abstract mathematical objects could exist all the same, even if there wasn't anything physical. If we imagine that the physical universe simply didn't exist at all, it seems like it doesn't have anything to do with the mathematical object. So one can't define the physical objects as the mathematical one. It doesn't seem like it's the same thing to me, because I can imagine the physical things not existing even when the mathematical objects do. Like, just because, I mean, if we can imagine Shakespeare never having written Hamlet, but still Hamlet would exist as this abstract thing in the world in which it hadn't ever been realized. Okay, but I could imagine the entire physical universe having that status, right? So it seems like there's something more that you have to say about what does it mean to exist physically that I don't think these mathematical accounts really touch upon at all.
Okay, well then, since you would not provide me a wave function related explanation of life and existence, I want to ask you, what is your personal uh, belief when it comes to the meaning of life?
Oh, I see. Yeah. I mean, I guess it's funny how in English we can put words together that seem to have a meaning and refer to things, but they don't actually, right? Like, for example, Russell talked about this in his definite descriptions. When one of his examples is the King of France, right? Well, there isn't any King of France, but we can form the sentence, the King of France, and we can make sentences like the King of France is bald. And Russell was puzzled with giving an account of how the logic and semantics of such assertions work when the definite descriptions that they contain don't refer, right? And so maybe it's similar when you ask me something about the meaning of life, because the question itself is sort of presuming that there is such a thing as the meaning of life. And that's not something that I'm totally convinced of. I mean, I can tell you what gives my life meaning, and it would have to do with the ideas I'm thinking about and that have inspired me, and about friendship and companionship and interactions with other people, and all of the things that I find most rewarding about my life, right? And so, but I don't know that there is a thing that is the meaning of life, and that we could sort of explicate. I could just tell you what I have found meaningful in my own experience of life. But it would just be all the same things that anyone would say, one would think, the things that are enjoyable and that seem to make life worthwhile living, and so forth. So, I'm sorry, that's not a very good answer, but that's what I think.
Okay, okay. Could artificial intelligence win a Nobel Prize or a field medal in the 21st century?
Oh, I see. That's quite interesting. I mean, it's quite exciting times that we live in, where there's these amazing and rapid developments happening with AI. Um, and and I don't see any reason to think that they won't continue to be extremely successful. I find this quite exciting. Um, I, I also find, for example, these LLM models, I think, well, they're very impressive in certain ways, but in other ways, they're actually quite disappointing. And so I wonder if that method has maybe already achieving its limitations. I mean, so I think there will be fundamentally different architectures that will be required in order to do the kind of thing that you were just referring to. Like, particularly if you look at, say, how the chat programs and so on, I mean, they're very impressive at writing essays that are sort of well written and coherent and so on. But they're absolutely terrible at producing mathematical arguments. I think it's completely unimpressive, actually. If you ask these chat programs to prove a theorem, if it's not a theorem that's like all over the internet and part of their training data already, like a new theorem, even a very minor one, a simple one, then they're going to screw up. It's going to be wrong. It's going to be nonsense. And the most infuriating thing about it is that they don't admit they're wrong. They don't say, I don't know how to prove that. They'll give you some argument, which is garbage. And they'll say, here's a proof. But it's not a proof. It's just wrong. They make mistakes and so on. And if it were a person doing that, I would find it infuriating to talk to a person who keeps, or for example, I've been using one of the standard chat things which I subscribe to produce nice AI images and so on, which I use in some of my Substack postings and so on. I find it quite nice. But it's aggravating sometimes when you're saying, well, I want an image, like this. And it doesn't do it. And you say, you reply back, I wrote back, could you please write the word clock on the clock face of the clock, and it gives you an image back. And the description underneath says, here, I did it. I made an image, like you said, with the word clock written on the clock face, but it isn't there. And or for example, I made an image of stock traders in the platonic realm looking at a graph, like stock graph, because I'm writing this essay, as I said, about the perfect prediction theorem. And it put a bunch of computers in the image. But it's like these ancient Greek people in the academy with this stock graph on the wall, but they have laptops And so I wanted it to get rid of those laptops. And so I asked it in all kinds of different ways to get rid of those laptops and because there shouldn't be any computers in the image. Um, and it would say, oh, I got rid of all of them, but they're still there. And so it's so frustrating, this kind of lying. I view it as a kind of dishonesty that in a person would be disqualifying for continuing the conversation. If there was a person that you were talking to and you asked them quite explicitly to do a certain thing and they tell you back, oh yeah, I'm doing that thing right now, but they're not, then you would stop interacting with that person. It would be so aggravating. Okay, but meanwhile, I guess we have to be more forgiving of these chat things, and they in certain respects, maybe it's that I have to learn how to give better prompts and so on. I suppose that's the real answer. If I make the prompts in a certain way, then then the things will produce exactly what I want, I suppose. And that's probably true. I'm sure I could improve. But in terms of producing mathematical argument, they're not very good. And they haven't even met this hurdle, which I often talk about with students, namely, when a mathematician is starting out as a student, then one of the first things you have to learn as a mathematician is whether you have a proof or not. And that you shouldn't write out an argument that isn't a proof. If it's not a proof, then it's better to just say, I don't know, than it is to give something that you know isn't right. And the AIs aren't even at that stage yet. They haven't made this hurdle yet of knowing whether or not they have a proof. And usually they don't. But they present it as though they did. And that's not right. It makes it not useful to talk to them. They make stuff up and it's wrong. And in mathematics, that really matters because we can't be misleading people thinking that you have a proof when you really don't. But okay, to address your question though, I think, yeah, things will improve, but it won't be on these LLM methods. It's going to be some other technology.
Surely, some improved
Maybe it's
version.
going to be combined with the LLMs because they're really good at making a coherent essay and explaining things. But there has to be some other way of ensuring logic and truth and so forth. And maybe there will be eventually. I'm just not sure what it will look like.
Okay, do you believe instead that for this general sort of artificial intelligence, will they ever reach the conscious phase where, like human beings, they will be able to assess and grasp their own mortality and their own finiteness, which is something that animals, for example, I believe I've read they do not share with us. A dog does not know of its mortality, of its incoming death. Do you believe that this aspect of consciousness is computable?
Yeah, I think I do. I think I don't see any reason why not. Also, I don't necessarily agree with your claim about animals. I think that animals probably know a lot more than we think. So I just taught a class on the philosophy of computability, and we read Turing's paper on the Turing test and so forth, and follow-up papers and so on. And students made presentations with papers that they found, and one of them was a paper by Manuel and Lenore Bloom on giving an account, a formal account of what it means for a system to be conscious. They're sort of trying to identify the fundamental processes. I don't remember the paper title, but it's something like Turing machines for consciousness or something like that. It has nothing to do with Turing machines, but rather they're trying to describe in a kind of engineering way what it means for a system to be conscious, to have consciousness. And part of it is that, well, there's these different kind of computational modules which can talk to each other, but only in a limited way. So there's like a short-term memory, and they can compete with each other to put things into short-term memory, and everybody can read the short-term memory. And so, and then there's this kind of slightly higher level thing that's deciding which of the modules gets to be activated in terms of the input that's coming and so on. So there's this whole kind of architecture that they describe, which has these features that I just mentioned. And in principle, this would be a kind of computational approach to consciousness, and that what the consciousness consists of is having an architecture of this kind of form. This is what their paper is about, trying to identify those features. And part of their argument is that, well, the mere fact that, say, a Turing machine, which is Turing complete, of course, by definition, can simulate such a system doesn't mean that the Turing machine doing it would be conscious. This is a very important point, I think, that they make in the paper. It's a minor point, but it's very important. Just because you have a computational process that simulates a conscious thing doesn't mean that it's conscious, because it might not have the right architecture. The simulation is doing it, in series or something, but this sort of parallel nature and the particular way that the things are interacting in their model might not be respected by some other computational process that's simulating it. So I thought that was a very interesting idea. Which seems almost certainly right. And so if it will be that computers become conscious, then it will be because of some particular structural features that their architecture has that will be important, and that not every computational manner of simulating the whole system is going to have those features. And so therefore, this point can be used to criticize some of the other accounts of what it means to be conscious that exist in the literature. I find it quite interesting. I guess I fully expect there to be this kind of AI coming into existence in the future. I mean, we're not there yet, but we're getting closer, and it's quite exciting what's happening.
What is to you the most beautiful idea in mathematics or the philosophy of mathematics?
Oh, I see. The most beautiful idea is, well, I'd have to say that it's the study of infinity and the different facets of infinity and the different sizes of infinity and different kinds of infinity has just been fascinating. I mean, to me, it comes up in so many different ways. It's just beautiful, like working out how all these different ideas about infinity are connected with one another, not just in terms of sort of Cantorian sizes and so on, but there's for example, in the theory of infinite games and so on, or in the analysis of potentialism versus actualism and so on, these different interplay of different conceptions of the infinite. It's just so amazing and beautiful, and it's definitely my favorite.
Thank you for this conversation, Joel.
Oh, yeah, sure. It's my pleasure. Thank you for inviting me. Yeah, pleasure to be here.
This was a conversation with Joel David Hamkins. Thank you for being with us. I hope you have enjoyed it. This was Back to the Stone Age.